Okay, so all of that was context for... What was I complaining about again? The timing was so bad. I don't know how it even worked. Oh, right. Clock domains. Doing all this for a single clock is pretty straightforward. Managing multiple clocks is less straightforward. If your logic doesn't touch something with a different clock, you're fine. The problems occur because they frequently do. Remember that setup window I kept going on about? The signal gets clocked in at the source register, held for some amount of time, and then has to propagate quickly enough to be accepted by the destination register. We had a nice, simple equation for it. Well, what happens when we don't know when the source register is clocked? Problems. Problems happen. The biggest problem is that the clock could give you enough time. It could work. Some people just don't think about it, and everyone else decides they can too clever by half it in their omniscient knowledge of a design they're not even going to simulate. And it is theoretically possible that the design has been so explicitly architected, so carefully constrained, so delicately orchestrated, that the signal will always arrive in time. This is one of the siren songs of engineering. Another, integration will be easy. This time, it won't be. Some of the time, that signal will miss the setup or the hold window, and the destination register will end up in an indeterminate state, i.e., it won't work. Sometimes I press the button and it doesn't work. If that happens, just hit the button again and the data should come through. Look, the problem isn't that this clock domain crossing exists. CDCs are a fact of life. It's a fact of life that your data is going to have to go from a highly optimized, beautifully pipelined, steady data stream into DDR or a computer of some sort. The problem is that the CDC is just a wire carelessly strewn across the boundary of the two domains. So handle it. You got to do two things. Two things. Add synchronizer circuits to your design and explicate that clock domain interaction in your design constraints. The problem is that the destination register might not have time to change state, which turns everything downstream into garbage. There is a very simple solution to this. Give it more time. Now, the only knob we have in terms of time is the number of RTL units. Each unit adds one clock cycle of latency. So we can stick an extra register with zero combinational logic between the source and destination registers on the destination clock domain. The theory is that if we stick these close together, there will be a negligible travel time for this intermediary signal. So even if the first register ends up in an unstable state when the first clock hits, it'll figure itself out and get its act together well before that second clock hits the structure. The second register will most likely be A-OK. And that is a probabilistic determination. You have a set of possible combinations of inputs, the phase of each clock, signal travel time, switching time. Some of those combinations produce good results, and some break your system. So you can characterize this mathematically by computing the mean time between failure, or MTBF, but that's a tangent. That involves math. You can add more stages to gain robustness at the cost of clock latency depending on how certain you want to be, which is what the MTBF is for. If you're working with an FPGA, there's most likely a recommended number of stages to use. Or you have no clue what the original designer was thinking because he used an alias to connect a data signal between clock domains. So you just use a 2 flip-flop synchronizer. Which reminds me, data buses are a bit special. Multi-bit buses are a bunch of single buses that are related to each other. Francisco, that's obvious. So what? Well, we think about each bit of a multi-bit bus as having an identical path through the design, because RTL-wise it does. In reality, there are slight differences in the travel times. So while a single bit is perfectly fine, another bit might have a problem. This window of acceptable relative clock phases is slightly different for each bit. But you want to guarantee that all the bits are correct at this output so that your data is correct going into the next compute stage of your pipeline. A 2 flip-flop synchronizer only guarantees that its output bit will probably match the input voltage held around the clock event 2 or 3 cycles ago. It has nothing to do with the other bits. If only one bit changes at a time on the input, you don't have to care about the other bits either. And sometimes this is fine. For a counter or a state machine, you can encode the value so only a single bit ever changes between clock cycles. The other bits are constant, so their registers don't change, so the transistors are never at risk of being caught with their pants down. If you have a data bus where multiple bits may change, it's possible that one of the registers falls behind and the output does not match the input. So to ensure the data is correct on the destination side, we need to add additional logic. We want to manually hold the data on the input and send a valid signal or pulse through its own synchronizer that tells the register on the destination side, the data is good, register the new data instead of holding the previous value. For example, a recirculating mux synchronizer. Now, you might say, Francisco, that sounds complicated. Putting a 2FF sync on each bit should be fine, right? Yeah, probably. Now we're talking about robustness in your design and the difference between making something that can work and making something that will work. Everyone's been in a situation where you hit the button and nothing happens, and the operating procedure is hit the button again. That's frustrating and it's not always acceptable. Also, maybe one of your registers gets hit by radiation and is partially compromised, or a radiant electron pushes it into metastability when it otherwise shouldn't be. Now that extra robustness is very valuable because should work on a bench becomes kinda works in the field. So it's worth the extra effort. And for a data bus, that effort is significant because there are requirements imposed on the transmission side. That data has to be held for a certain amount of time. The logic that's holding the data also has to generate that control pulse. Maybe you go even further and you add an acknowledge pulse from the destination back to the source to release that lock on the source register. You can't just launch a constant stream of data. Now you need state machines and data buffers, and you have to think about data rates and data flows. And if you don't think about that up front, you construct your design in a way that is inimical to adding that logic later on. Then you just have to YOLO 2FFs all over the place and hope it works. Please, please think through your designs carefully and pay attention to some of these niche considerations. It's easy to regurgitate HDL, but that will frequently create a big mess when you put it into hardware. A mess one of your coworkers, several years down the line, will have to spend months struggling to unravel because it was checked into a common repo and he made the mistake of looking at the timing reports, and now he can't just ignore it, right? It just has to be good enough to work, I guess. Anyway, I hope that was interesting. Think through your designs because thinking is where the engineering happens, not when you're typing into an editor. I'm going to go sleep now, so you have fun.